let's talk about scalars and vectors. The difference between scalars and vectors. Does anyone know? Scalars, vectors. Do I think it's a good thing that we have an equation sheet? Yes and no. It's useful for you guys, but it just means you get less marks where they ask you for the equation. You'll see when we do some questions, you get a mark for actually stating an equation, but you probably won't get those questions anymore because they give you an equation sheet. Yes, perfect. So scalars only have magnitude. Vectors have magnitude and direction. So what do we mean by that? Magnitude is basically size. So something you can measure which has a size. So for example, the length of something, you use a ruler to measure the length of something. That's a scalar because you don't give the direction. When you're measuring the length of something, you're not measuring the direction. You're not saying that's 10 centimeters to the left or 10 centimeters to the right. So a scalar, an example would be length or distance would be an example of a scalar. Vector has to have a size and a direction. What are examples of vectors? What do you guys think? Or giving you some more examples of scalars if you guys know, whatever you think you know. Velocity, yes. Any force, good. So forces, any force is a vector because force depends on direction. You know, when you draw force diagrams, you always put an arrow to point what direction it's acting in. Another one is velocity. Velocity is like speed, but a vector version of speed. So speed is a scalar. It doesn't have a direction. When you're saying the speed of a car, you say that car is traveling at 60 meters per second or miles per hour. If you want to give the vector of the car, you have to give a direction as well. So 60 miles per hour, north or to the left, something like that. Acceleration is another one someone mentioned. Yes, it is. Acceleration is basically the rate at which velocity is changing. So if something's accelerating, it's getting faster. You give the direction for acceleration. So it can be negative as well. It can go backwards, it can go forwards. Displacement is another one, yes. Displacement is basically distance with a direction. So when you give the displacement of something, you have to give what direction it's acting in. Excellent. All right, so we got some good examples there. So let's start off with that. Let's go on to the question then. So velocity is a vector, speed is a scalar quantity. Describe what is meant by a vector and scalar quantity. Easy 2 marks there. You just need to state what we've said there. So for vector quantity, you would say has magnitude and direction. Scalar quantity has magnitude only. So I did that without even reading the question. Let's read the question. So figure 8 shows a girl bowling a ball along a 10-pin bowling lane. Okay, so the ball is going down and she's trying to knock down 10 pins at the end. And they've given you this introduction question, all right? So on to the next one. Explain why the bowling ball decelerates as it travels along the lane. Deceleration. What does deceleration mean? If something decelerates, what does that mean? So it's the opposite of acceleration. So if something's accelerating, what does that mean? And if something's decelerating, what does that mean? This is for for combined and for triple. Yeah, slowing down. So deceleration means it's slowing down. Accelerating means it's speeding up. In terms of the values, they're both measured in, so the units for acceleration is meters per second squared. If it's a positive number, a positive value, then it means the object is accelerating. If you get something like minus 10 meters per second squared, then it means it's slowing down, it's decelerating. So you guys are commenting. I'll try and reply to your comments, guys. But if anyone knows the answers to anyone else's comments, just answer back. I'm trying to reply. Hi, this is how higher and foundation. So, question: explain why the bowling ball decelerates as it travels along the line. I think someone said the answer, but what do we get the 2 marks for? Why does it slow down? It's basically saying, why does the bowling ball slow down as it's rolling down, basically? Friction, good. We should mention friction. Friction acts on the ball. That's 1 mark. What do you think the second mark's for? You're given the formula list just for physics. You give a formula sheet just for physics. You don't get one for chemistry. Chemistry, you just get a periodic table, and biology, you don't get anything. So friction acts on the ball. That's one of the marks. I don't think anyone said the second mark yet. What makes it slow down? What else is it about the friction that makes it slow down? No one? Air resistance. You can say friction and air resistance here if you want. They're both acting on the ball, so they're both worth the first mark. The second mark is, yep, someone said that. It's opposing force. It's acting in the opposite direction to the movement of the ball. Well done, guys. So because it's acting in an opposite direction, it's going to slow the ball down. It's going to give it a smaller resultant force. All right, next. Write down the equation that links mass, momentum, velocity. So this is the type of question I told you guys you probably won't get because you get the equation sheet. 1 mark, but that's here in our equation sheet. So I very much doubt they're going to ask questions like this because it's literally reading off the equation sheet. Momentum is equal to mass times velocity. So momentum is a higher only topic for those of you that want to know. So you can write that, or you can write it as letters as well. You can get away by writing it with letters as well. P equals mv. This is combined, yes. Everything's relevant for combined and triple. Right, next one. So in these questions, they've kind of given you a clue that this question is going to be about momentum. So here, they actually state momentum, so that's another clue. What equation are we going to use? Literally the one that we've got here. We want to calculate the mass. How do we rearrange that to make mass the subject? We want to calculate the mass. So we've been given the velocity and we've been given the momentum. So we've got velocity, momentum, we want to work out mass. So we want to rearrange the equation. So the triangle for this, if you guys do use the triangle method, looks like that. So mass, cover up mass is Momentum over velocity. Yep, thank you. So I would say to people, always write your working out. Even if you think it's an easy calculation, I always tell people to write their working out. If you get the right answer, that's fine. You will get all the marks, but just in case you make a small mistake, you can still get the marks from the working out. So 3 marks here, 2 of them are for working out, 1 is for the final. So if you were to accidentally type something wrong in the calculator, you could still get the other 2 marks, 2/3 of the marks just for writing the working out. So that's why I always tell people to write the working out. So let's sub in the values here. We have 26 as the momentum and velocity is 5. So we do 26 divided by 5. And the answer is, it's not going, I'm going to put this on my YouTube page, not a TikTok page. This is higher. Anyone got the answer? Anyone got a calculator on them? 26 divided by 5. Yep, thank you. 5.2 kilograms is the answer for this one. 5.2, excellent. Moving on. Explain why the bowling ball slows down when it hits the pin. You should use your ideas about momentum. What do we know about momentum when a collision happens? So momentum is mass times velocity. Any object that's moving has momentum. So any object with mass and is moving, so and has a velocity, has a momentum. And yep, thank you. Momentum is conserved. That's one important thing about momentum. It's like energy. You guys, hopefully you know, energy can't be created or destroyed. Same thing with momentum. Momentum has to always stay the same. So when anything happens, whenever a collision happens or something, momentum before should equal momentum after. So back to that question, when the ball hits the pin, what's going to happen? So let's say ball here, pin, I'm going to draw like this. The ball is moving in this direction. It has a velocity and it has a mass. So it has a momentum. The pin has a mass, but it doesn't have a velocity. At the start, it doesn't have a velocity because it's just staying still, isn't it? But then the bowling ball comes in and hits the pin. So what's going to happen? Why does the bowling ball slow down? Why does that affect the bowling ball if it hits the pin? Momentum is transferred. Yes, good. Momentum is transferred to the pin. So the pin is going to increase in momentum, right? At the start, the pin has no momentum, but when this hits the pin, it's going to gain momentum because it's going to move. The pin's going to move, so it's going to gain momentum. So 1 mark is to say that momentum of the pin increases. And then you get a mark for stating that thing that we wrote in our notes. The fact that momentum before is equal to momentum after, or momentum is conserved. So you can say that for your 2nd mark. So momentum of the pin is increasing. Momentum needs to be conserved. So think about that. If momentum needs to be conserved, the momentum of the pin increases. That means the momentum of the ball needs to decrease. So in other words, it's giving its momentum to the pin. So that means the bowling ball is going to get less momentum. And in other words, that means it's going to slow down. It's going to have a lower velocity. So you can say, therefore, the momentum of the ball will decrease. And in turn, that means the speed of the ball will decrease. Conserved, what do I mean by conserved? I mean, it's never lost. You can't create or destroy momentum. It has to be the same before and after. So the total momentum of both objects added together should always be the same. So at the start, this one might have momentum of, 10, let's say it's got a momentum of 10 kilograms meters per second. This has 0 at the start. So that's before the collision. This has 10, this has 0. After the collision, the pin moves. If you hit a bowling ball into a pin, it's going to move, right? So it's going to get some momentum. Let's say it gets 3. This has to be conserved. In total, it needs to have 10. So this one, the bowling ball, will have 7. So basically, the bowling ball's gone from 10 to 7 meters per second, so it's slowed down. I hope that made sense. So yeah, think of it like energy. Good stuff. All right, next question. So in figure 7 shows air-powered rocket, and it's been launched vertically upwards. So we've got a rocket going upwards, an object going upwards. And then how does the velocity of the rocket change as the rocket moves upwards? What do we think? Imagine something being thrown upwards. Loads of people make a mistake here. What happens to the velocity? So some people are saying increase, some people are saying decrease. So yeah, it's definitely not staying the same. Yeah, more people are saying decrease. Thank you. It is decrease. It's decrease. You might think it's increasing because you're throwing something, so it feels like it's going fast. But here you're not even throwing something. But the moment it starts moving upwards, after whatever's giving the force upwards, the air power, after that stops, from that moment it starts to slow down, because it's basically doing this, isn't it? It's going up, 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 up. And then it's coming back down, 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 and down. So at some point here, it's going to go to 0. The velocity is going to go to 0. It's going to stop. So from this point onwards to this point, it has to go from a speed to 0. So it has to slow down to get from this point to that point. So how does the velocity of the rocket change? Decreases. Now, how do we explain that for the second mark? Air resistance, yeah, we can talk about air resistance. What's air resistance doing? So you can't just say air resistance, you need to say something about air resistance. Similar to the bowling ball one, for why it's slowed down, what did we say? We said friction, and then we also said it's opposing, it's acting in the opposite direction. Exactly, yeah. So air resistant acts in the opposite direction. Well done, guys. Good. All right, next question. The velocity of the rocket is not the same as the speed. What's the difference between velocity and speed? So we talked about this right at the start of the session. Weight, yeah, you can talk about weight as well. So air resistance acts in this opposite direction. You can also mention weight because that's also acting downwards. And in fact, they actually tell you weight is going downwards, air resistance going downwards. So you can talk about both or either one. Yes, next one is right. So we've got speed only has direction because it's a scalar. So speed is a scalar, only has a direction, it has a magnitude. And then velocity is a vector, only has, has a magnitude and direction. That would be your marks. This is combined and triple. All of this, everyone needs to know. On to the next one. The speed of the rocket just after being launched is 12 meters per second. The mass is this. Kinetic energy. Right, what's the equation for kinetic energy, guys? We've got it here. Kinetic energy equals half mass times speed squared or velocity squared. Half mv squared. Kinetic energy equals half mv squared. Yeah, so the fact that they asked you to calculate kinetic energy, that's what you need to look for. Yeah, well done, guys. So let's sub in all the numbers. So half times, what's the mass that we've got here? The mass of the rocket is 0.05 kilograms. Remember to show you're working out. Times v squared is 12 squared. So don't do squared of everything. It's only the v that's squared. That's a mistake that people make. They do half times 0.05 times by 12 and then they square it. So you need to do the 12 squared separately and then you need to times them all. So it would actually be 144. So half times 0.05 times 144. Does anyone have the answer to that? 3.6. Yes, it's 3.6. So the answer is 3.6 joules. Not 7.2. I think if you got 7.2, you probably forgot to half it. So remember to half it. You might have just done mv squared, I think. Yes, you do get your formula sheets paper for combined for OCR. Yep, you do. Everyone gets their equation sheets this year. Only for physics, not for the other two. Okay, good. All right, next question. As the rocket moves upwards, it gains gravitational potential energy. State the maximum GPE gained by the rocket. Ignore the effect of air resistance. What do you think the answer to that is? Yeah, this is going to be on YouTube, guys. I'm going to upload it when I'm done. Not straight away, but sometime this week. 3.6. Exactly. Yeah, it's just 3.6. There's a clue here with these types of questions. When they say state instead of calculate, see here they said calculate. They expect you to do some sort of calculation. Here they've said state and it's only 1 mark question. So that means, and they've given you no lines to do the working out in. So that means somewhere the answer is here somewhere. You've either calculated it before or it's somewhere in the question. In this case, it's 3.6 because the rocket is moving upwards, remember? As it's moving upwards, its position, it's getting higher. Its height is getting higher. So its gravitational potential energy, that's something that depends on height. depends on height, is going to increase because it's getting higher. So what happens is, as it moves upwards, the kinetic energy decreases, so it gets slower and slower, but the gravitational potential energy increases. So kinetic energy gets converted into gravitational potential energy, and right at the top, all of its kinetic energy is gone. It's all been changed into gravitational potential energy. So whatever kinetic energy you had at the start, you had 3.6 joules of kinetic energy at the start, all of that's gone to gravitational potential energy. What happens after? It starts to fall down, doesn't it? When it falls down, it does the opposite. The gravitational potential energy, because it's getting lower in height, starts to decrease, and then kinetic energy starts to increase again. Those are the energy changes that happens throughout this whole thing. So yeah, the answer is 3.6. Calculate the maximum height the rocket would reach. And they've given a clue here. They've given us the gravitational field strength. That's G. G is equal to 10 newtons per kilogram. Sometimes you get it as 9.8. Some exam board gets it at 9.8. Some exam board gets it as 10. They'll tell you. So what would we do for this calculation? What equation do you think we'll use? They've said use the correct equation. So that means you have to use one of the equations from the equation sheet. So what do you guys think? Any ideas? Yeah, that was my daughter, guys. Sorry about that. Yeah, mgh. So GPE equals mass times gravitational field strength times height. mgh. So the reason why is because the maximum height, remember what I said, kinetic energy changes into gravitational potential energy. So if you know the gravitational potential energy at the top, which we do here, we know it's 3.6, we can use this equation to work out the height. So we want to rearrange this equation to work out height. So what happens if you rearrange that? H is equal to... Thanks, guys. How can we rearrange this? Divide by mg, exactly. So energy divided by mg. So we know the energy from the previous question is 3.6 divided by mass. The mass, we know the mass of the rocket was here, wasn't it, as 0.05. So we do 0.05 times by g, which if it's in the question they say 9.8, use 9.8. Here they've told us it's 10, so we'll use 10. But in the mark scheme it says if you use 9.8, it's fine as well. So you would get marks for both. What does this give? Can anyone calculate it? .2. Thank you, guys. So it would end up going to 7.2 meters. 1.8. I wonder how you got 1.8. I think you accidentally times it if you got 1.8. You're supposed to divide it. So do 3.6 divided by this. If you got 1.8, you might have accidentally times it. Okay, well done, guys. So on to the next one. So here we have a person using a jetpack water is forced downwards. So this person is on the jetpack. Water is forced downwards and it produces a force upwards. So the force of the water, even though the water is going downwards, the force that it's creating is upwards. So we have the force from the water. So I'll call that F water. And then downwards, you have weight acting on the person, because weight always acts on anything with mass. So state the condition necessary for the person to be able to remain stationary in midair. So we need to talk about Newton's 3 laws here. Let's talk about that. Let's add that to our notes. We have Newton's first law, Newton's second law, and Newton's third law. Anyone know what the first law is? So it is, it's to do with resultant force being 0 or balanced forces. Stationary or constant speed, yes. An object will stay in motion or rest unless disturbed by outward resultant force. Okay, that's one way to say it. So basically, if forces are balanced, or if there's no resultant force, if there is no resultant force acting on an object, it will remain stationary or travel at a constant speed. So that's Newton's first law. If that's the first law, the second law is basically the complete opposite of the first law. So it's when there is a resultant force. So what would that be? So if there is, let me give myself a bit more space. If there is a resultant force, it's F equals ma. So if there is a resultant force, what does that mean? So F equals ma is an equation to describe Newton's second law. It basically means if there's a resultant force, F means resultant force, then the object will accelerate. So if there's a resultant force, the object will accelerate. And it will always accelerate in whichever direction the force is acting in. So it will accelerate in the direction of the resultant force. Okay, so acceleration is proportional because F equals ma. Acceleration is directly proportional to force. Okay, so based on that, let's go back to the question. So we've got state the condition necessary for this person to remain stationary. So what law are they going to talk about? Newton's first law is what we're going to talk about. So we need to basically state Newton's first law. How is the person going to stay stationary for 1 mark? What would we say? It's not to do with momentum. So we can't just say Newton's first law for our answer. We need to apply it to the question. Forces are equal. Yes, exactly. No resultant force. You can either say no resultant force, forces are equal, or you can say the upward force is equal to the downward force. Any of them will get you the mark. So no resultant force. Well done, guys. Next one, we got a question. with a calculation this time. The person weighs this much, jetpack weighs this one. Calculate the combined mass of the person and jetpack. How can we do this? What equation I'm going to use here? So we've got force, or it says weight, weighs, force or weight, and they're basically giving us a clue that we need to use something with G in it. So yeah, good. Some of you are getting it. So you look for the right equation with weight and gravitational field strength, because they've given that to us and they're asking us for mass. So we need to use the equation W is equal to mg. And we need to rearrange that. How can you rearrange it? So, sorry about that, guys. M is equal to, this one is AQA. Thank you. How can we rearrange this? M is equal to, no one? Weight divided by G. Thank you very much. Weight divided by G. So we need to sub in our weight, which people get confused because they'll think it's 700 or they'll put 140. We've got two weights here. What do we need to do with that? So we need to use W equals mg. Yeah, we need to add them together because it's a combined mass it's asking for. So we need to do 700 plus 140 divided by G, which is 10. And that gives an answer of what? Wait, for 7a, would you get the mark if the forces are equal? Yeah, if you said forces are equal, you would get the mark for the previous one. Yeah. Excellent, guys. 84 kilograms. That becomes 840 at the top. 840 divided by 10 gives you 84. Well done, guys. All right, next one. Increasing the upward force to 1,850 Newton causes the person to accelerate upwards. Calculate the acceleration of the person and the jetpack. What equation do you think you need to use here? This isn't foundation. These are higher questions. There's a mix. One of them was from a few years ago. This one's a bit older. So let's look at our equation sheet. You tell me which equation you think you need to do here. So we got a force, F equals ma. Yeah. So it's not V minus U over T. It's F equals ma. Where's that? That is down here. F equals ma. So what will we sub in here? Because that's not straightforward. We want to work out acceleration. So acceleration is force divided by mass. And then if we do that, then acceleration is equal to, what's the force that we're going to use? That says 1,850. I think that's what you mean. That is not actually the number that you're supposed to use. You're not supposed to use 1,850. That's a trap that loads of people will fall into. What do you guys think then? We're increasing the upward force to 1,850. Let's remind ourselves. Remember, there's the upward force of the water, and there's the weight of the jetpack and the person. You don't add it together either. Exactly. Thank you. You got to minus it. Why do you need to minus it? So upward force in the question says it's 1,850. So this force is going to be 1,850. The downward force is what? What's the downward force going to be? Not 84, 840. 840, yeah, because we know the weight of the person is 700 and the weight of the jetpack is 140. So we add that together and we get 840. So the reason we need to minus them is, in F equals ma, what we put up here in our notes was F here is resultant force. So remember that F is resultant force. It's not just any old force or the forward force. It's always the resultant force. Resultant means the overall force. So you can only use this equation if you use resultant force. So in this example here, it's going to be 1850 minus 840. So 1850 minus 840, that's our resultant force. Then you divide it by the mass. The mass was what we calculated earlier, which was 84. So we do all of this divided by 84. Does anyone have an answer? Yep, so 1010 divided by 84. Excellent. What does that give? Yes. Thank you, guys. 12.02. You can get away with saying 12 for this as well. This one, it asks for the unit as well. So this is why I tell people you need to know the units. This equation sheet does not give you the units. It just gives you the equations. So here you'll get a mark. So I think in these papers this year, they will probably do this because they're not going to ask you for equations. They might ask you for units, but we'll see. 12.02 meters per second squared. Good. So you have to put the squared in there. You can't just leave it as meters per second. Well done. On to the next one. Here's another equation that links acceleration, mass, and F. We know that F equals ma. Like I said, you won't get questions like this year. I doubt it because they give you the equation sheet. This is just applying. What do you guys think? Why is it squared? That's just the units for acceleration, meters per second squared. Can you go back for a second? Yeah, let me go back for 1 second. Remember, I'll be putting all of this up on YouTube, guys, if you want to rewatch them. So just go into Flash Revision Lab. I've got all the ones from last week. So you just go onto it and got a document. That's all the questions that we do. So you can watch the video and you can follow it as you and try the questions as you go on. And I've got some other videos on it as well, on other topics. So this one's how to write chemical formula, for example. And I'll be trying to make some more this week as well. I think some of you guys asked for one on balancing equations. I'm going to try and do that at some point as well. So yeah, Flash Revision Lab, if you want to watch this again. So back to this. Sorry, you guys wanted to see this. Any questions on this one? This one, there's no Edexcel questions, no. But I do, in some of the sessions, there were some Edexcel questions as well. But it's relevant to everyone, these types of questions. The app's name is GoodNotes. Okay, we're done. Right, so we use F equals ma here. We're trying to work out the mass. Mass is equal to F over acceleration. When we rearrange that, so we just sub the numbers in. We got 0.63 as our force and acceleration is 2.1. 0.63 divided by 2.1. Anyone got the answer? Yeah, well done guys, 0.3. Right, next question. This is a question on springs, still part of forces in motion. This is later on. So we got keyboard here. Underneath the keyboard, there's a spring. So that's why when you press it, it comes back up. The springs behave elastically. So it's elastic deformation. What is meant by elastic? So you can have elastic or inelastic, or you can call it plastic. Yeah, I have done electrolysis. There's a video of that on YouTube. We did that last week, electrolysis. Last one, yeah, it means the spring will return to its original length when the force is removed. So you stretch it or compress it, and then if you remove the force, it'll come back to its original shape. That's elastic. If it's inelastic, or we also call it plastic, it means when you stretch it, it stays stretched and permanently deforms. So just two properties that should be the same for each spring. So remember, they're talking about the springs underneath the keys in the keyboard. So when you push it, it needs to come back up. What properties do you think needs to be the same? Same length, yep. Good, well done guys. Same length is one of them. And spring constant. Yes, well done. Same spring constant. They basically need to stretch the same amount. They need to have the same compression when you press them. So that's basically spring constant. How stretchy it is, how compressible it is. Same smell. Not quite. Okay, so here we've got one of the keys. We've got the spring here. And the key must be pressed with a minimum force of 0.8 newtons before the key touches the switch. So basically, let's look carefully. There's a distance of 0.004 between this bit and this bit. So this needs to touch that in order for the key to register. That's the distance it needs to move. Calculate the spring constant. So here, what equation I'm going to use? This is a more recent paper, I think. I forgot the year. I think it's maybe 2020. What equation? So the one it's definitely to do with springs, isn't it? So which ones do we have? We have this one here, elastic potential energy. Not that one, because we have no information about energy here. We need to use something to do with distance. We've got distance here. We've got force here as well. Yes, the Hooke's law one. So Hooke's law, it's not given as Hooke's law in the equation sheet. What is that? Which one's that? Yep, thank you. Force is equal to spring constant times extension. This one here, F equals KE. So F is the force you apply, K is the spring constant, and E is the extension. It doesn't always have to extend. It can be compression as well. See, this one is not extending. It's actually getting smaller, but you can still use that as the extension. So rearranging that, K is equal to force divided by extension. So the force is 0.8 divided by our extension, which is 0.004. Good. And what does that give? Yes, this is combined. Good. 200. So answer is 200 Newton meters. Well done. Next up, so this is a question about spring. This time it is being extended. So you got a spring being hung from a support. The spring is stationary and has been stretched beyond its limit of proportionality. What does that mean? If it's stretched beyond its limit of proportionality. Yeah. So it won't return to its original extension. So which ones will it be? The spring is inelastically deformed. Good. So that's the opposite of the first one. It's been inelastically deformed. It won't return back when it's reached that limit. What's the second mark for? Fourth one, nope. It can be stretched. It doesn't necessarily mean it can't be stretched any further if it's gone past its limit of proportionality. That doesn't mean the maximum. It's just it won't return back. So it's not the fourth one. It's the third one. Why is it the third one? The upward force of the spring is equal to the downward force. Why is it the third one? Anyone know? It's to do with Newton's laws. Yeah, we got it. It doesn't move anymore. This isn't moving. The spring is stationary. Remember Newton's first law? If it's stationary, it means that the forces are, we did a lot. The forces are balanced, or there's no resultant force if it's stationary. So that means the downward force must equal the upward force. What was Newton's third law? Yeah, let's add that in. Newton's third law is when you have two objects in contact with each other. So let's say, for example, you have let's say you have a box on top of another box. All right, we'll call this one, let me draw that a bit better. We'll call the top one box A and the bottom one box B. Let's look at box A, right? Box A, the only force acting on box A is its weight. It's acting downwards, right? According to Newton's first law, if that's the only force acting on the box, it should be moving downwards. But it's not. If a box is on top of another box, this box A is technically not moving. And the reason for that is because the box underneath is pushing it back up. There's another force from the bottom pushing it back up. And this force, we call that the reaction force, is equal to the weight of the box, or the normal contact force. Is also known as normal contact force. Exactly. So the weight of the box A is equal to the reaction force that box B pushes onto box A. And because both of these are equal, the resultant force is 0, which means it's stationary. So that's why the box would stay still. I hope that makes sense. So the way you'd say that is, so one way you can state that in an exam is if object A exerts a force on object B, then object B exerts an equal and opposite force back onto object A. back onto object A. How does that link? It doesn't link. Someone just asked what Newton's third law is. We haven't used that in any of the questions here. It's just one, you might get a question on that. So I just thought I'd tell you. Wait, what was the last question? I forgot what the last question was that we did. Yeah, that was it. Yeah. I just wanted to say Newton's third law because we never mentioned it. But the upwards force is equal to the downward force because of Newton's first law. Newton's first law. So the weight of this is equal to, it could be the tension force. It's called tension when it's holding it up like that. And because they're both equal, Newton's first law is obeyed and it's stationary. Right, well done guys. So let's look back at the notes. I'll let you guys screenshot all of this for your revision. Anyone got any questions?